we first created a graph of a quintupling function where the value of y quintuples whenever x doubles. We started with 1, 2, 3, 4 values of x indicated in white here, just marked off in white, and 5 values of y. 3 of them are this value, and this value. The values of x doubled. The values of y increased by a factor of 5. That wasn't done perfectly. And we also had another value of y related to this one where y was 1/5 as great as this. It's going to be impossible for you to really sort that out because it's so close to the axis and to a point that I've marked here, namely the origin. But we get the white curve, which is close to the red curve. The red curve turns out to be a slightly improved model, and we won't worry about that at the moment. Based on the white curve, the original curve that we graphed, we then chose one point on the graph, not one of the points we used in constructing the graph, but a point that results from the curve that we drew through the constructed points, and we labeled that point 7,5. And I suppose an arrow would be appropriate. So the point is here. There are a lot of x's on the graph. There was a green x here, which projected down to the coordinate 7 and over to the coordinate 5. Now, all this so far was done without any of these numbers in green. Okay, only with the points that correspond to the white marked points on the x and y axis. Having then decided that this point was 7,5, it was an arbitrary decision according to the instructions of the problem. This was 7, this was 5, and then based on the fact that this is 7 and this is 5, we marked off the rest of the axis, and the same here. Using those markings then, we estimated the coordinates of 3 other points. We marked 4 points on the graph, 4 points in green, none of them the points that we used to construct the graph, and we chose the coordinates for this one, and then we estimated the coordinates for the other 3. And you can see those coordinates listed in green again, 1.9.6 here, 4.11.7 here, and 10.29.6 here. So here's a summary of our estimated coordinates. We also, at each of the points that we marked in green here, constructed a tangent line to our graph. And we estimate the rise and run between 2 points of each tangent line. And I've represented that in the yellow triangles here, except for this one where it would have been too cluttered to have done it. But in any case, I estimated the rise and the run and used that to find the slope. Slope here, rise was 3.8, run was 2.7. Dividing that, we get slope of 1.4. Here we have a rise and a run, which we divide in the appropriate manner to get the slope 1.9. Similarly down here, and did a similar thing here. And I get these values for the slope. And I label the slope y prime. Y with an apostrophe, read y prime. So here are the slopes. Here are the x values then, here are the slopes. Here are the x values, here are the y values. All of these are estimates. And then we constructed a graph, a straight line, we constructed a graph of slope versus x coordinate. We got these points. They don't lie perfectly on a straight line, but it's plausible that they lie in a straight line through the origin. There's a question mark on whether they do or not, and actually they come very close to doing so, but they shouldn't. Okay, if this graph was constructed correctly and all these quantities estimated accurately, we would not get a straight line through the origin. We wouldn't get a straight line at all. We'll talk about that. But it's not implausible, based on the construction we have here, that we do have a straight line graph of y prime versus x, slope versus x. Now, a little additional information. This completes what was requested on the problem, but let's put this into some more context. Okay, the quintupling graph would be of the form y equals ax to the p, and applying the condition that y increases by factor 5 when x doubles, with this form, we quickly obtain the relationship that 2 to the p should be 5 for this graph, which gives us p approximately 2.3, either by approximation or by using logs. And then, using the fact that the point 7,5, x equals 7, y equals 5, that point lies on the graph, we substitute the y and the x. We get 5 equals a times 7 to the 2.3, so that a is approximately 0.57. Now, elsewhere, we've gone through details of that on earlier problems on this particular series of documents for the final exam. We've gone over the specific details of the process that we would use here, so I didn't repeat that. But that gives us the equation y equals 0.057x to the 2.3 power. Using this equation, we evaluate y at each of these values of x, and we can compare the y values here and here, here and here, here and here, and here and here. And we find that the y values tend to run, our estimates ran a little bit high up here, a little bit low here. The red graph indicates the graph that we would have gotten from the actual curve, and we see that it should be a little higher here, a little bit low over here. So the graph should maybe have a little more curvature. And that would, of course, give us a greater slope up here. Slopes would be greater here, but a little bit less down here and here. So that would lower these points, these first couple of points, and probably raise the last couple of points. And that would result in a graph where maybe the slopes did this sort of thing, and we had some sort of upward curvature. Now, by the magic of calculus, and I'm not going to talk about the details of that except to say there's a very simple formula. Once you realize that this is a power function, it's a very simple formula for finding the y prime function, the function that gives you the slope of the graph, the function that gives you the rate of change of y with respect to x. Okay, there is the function. If we plug these x values in, we get these values for y prime. And we notice that this value for y prime is a little lower than this one. This is slightly lower than this one. This is slightly higher than this one. And this is significantly higher than this one. That kind of fits what we did with the graph here. And we see that that graph really should be, should have an upward curvature. And also a graph where p equals 1.3 is going to have an upward curvature. You could actually do 2 to the 1.3 power and see what the ratio would be for that graph. It would be slightly less than 3, I believe. And you could actually then construct this graph by using the appropriate y ratio with doubling of x. The key, though, is this construction, estimating these slopes, creating this graph in a reasonably accurate manner. Actually, obtaining the function and doing these comparisons was not part of the problem. That was included simply to draw this into a wider context and give you some idea of why this might be important.